Before beginning the lesson, please take out this handout so you can follow along. This is the beginning of our section on probability. So probability can be thought of in two different ways. One is called experimental probability. The other way of looking at it is theoretical probability. We're going to look at both, but in this lesson, the focus is on experimental probability. Now, the main difference between experimental and theoretical probability is that experimental probability is determined using results of an experiment or results of trials or tests. Theoretical probability, on the other hand, is determined based solely on possibilities. So if we're calculating experimental probability, this is the formula. The probability of an event is equal to the number of successful trials divided by the total number of trials. So you can express a probability as a fraction. You can change that fraction to a decimal, or you can change that into a percent. So a fraction, a decimal, or a percent, you can write a probability in any way you want. Regardless, the value is always between 0 and 1, or 0 and 100%. So just a note on proper communication here. P symbolizes probability, and then in brackets is the event or the thing you're measuring the probability of. If I wanted to know the probability of rain, my notation would be P and then in brackets rain. Now, the number of successful trials, what does that mean? Well, the trials are how many times you're doing the experiment. So for example, I can roll dice 10 times. So that would be 10 total trials. Now, if I'm looking for the probability of rolling a 3, then the number of successful trials would be the number of times I actually rolled a 3. So if I rolled a 3 4 times out of the 10 total times, the probability of rolling a 3 would be 4 out of 10. So I mentioned that a probability has a value between 0 and 1, or between 0 and 100%. So the extremes would be 0 and 100%. Probability always lies in the middle. So what do the extremes mean? Well, if you have a probability of 0 or 0%, that just means the event is impossible. If you have a probability of 1 or 100%, that just means that the event is certain. For example, if I asked what's the probability that a bachelor is married, you would say 0%. It's impossible for a bachelor to be married because by definition, a bachelor is someone who's not married. On the other hand here, if I asked you what's the probability that you are using electricity right now, you would have to say 100%. It's certain that you are using electricity right now because you're watching this video. So the whole point of doing these experiments or simulations of events is so that we can better predict the possibility of an event happening in the future. You see a lot of this in sports. With sports, you gather statistics, which are trials of experiments. And using these statistics, you can make probabilities. So you can predict who will win a certain game, for example. So the whole point of probability is to be able to make predictions. Now there's terminology that I want to go through, 3 different words, and these are the words. An outcome is a possible result of an experiment. An event is the set of outcomes that produce the same result in an experiment. A trial is one round of the probability experiment. So I want to illustrate this with an example. Let's say you're rolling 2 dice. Now, when you roll 2 dice, there's a lot of different possible numbers that you can roll. We would say there's a lot of different outcomes. The outcome could be you roll a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. Those are all the possible outcomes. Now, a specific event could be you roll a 3 and a 2. Well, that adds up to 5. You can also get a 5 if you roll a 1 and a 4. So these two outcomes gave you the same result. So we would say the set of all of these outcomes are the same event. The event is rolling a 5. And the trial would be each time that I roll the dice. So again, this is just terminology. I'm telling you this so that you know what I'm talking about when I use these words, and so that when you use these words, you're using them correctly. For this next part, if you have access to a die, a 6-sided die, you can do this. You can roll the die 10 times and record your results in a tally chart. So record how many times you roll an odd number and how many times you roll an even number. Keep track of how many times you do that, each roll, and then get your total for each. Once you have your totals, write out the probability of rolling an odd number and the probability of rolling an even number based on your experimental results. So if you have a 6-sided die, pause the video and try it and see what you get, and then check back in. So if you were able to do that, you'll count up how many times you rolled an odd number, and then to write the probability of rolling an odd number, you would take the number of successful trials, so that's the number of times you rolled an odd number, divided by the total number of trials. Well, you did 10 rolls, so it's out of 10. So you'll have a fraction out of 10. And you'll do the same thing for your even numbers. What's the probability that you roll an even number based on your experiment? And you can take that fraction and you can turn it into a percent. So let's just say, as an example, and I don't know what you got, let's say you got 3 odd numbers and 7 even numbers. That would mean you have a 30% probability of rolling an odd number and a 70% probability of rolling an even number. Now, what were you expecting? You were expecting probably that you would get about 50% for each, because there's the same number of odd outcomes and there's the same number of even outcomes. So you would expect the probabilities to be the same, of 50% each. Well, that leads into my next thing. If you're able to get results from some of your classmates or people sitting around you or near you, see what they got and add those up so that you have a higher total number of trials. So if you have your 10 trials and your friend's 10 trials, now you have a total of 20 trials, and you can see your 3 odd results and they might have had 6 odd results. So combined, you have 9 out of 20 as your probability of getting an odd number. If you're able to find more results, go for it and see what you get. Regardless though, I want to draw your attention to the bottom of the page. What we usually see when we have more trials, so we add your experiment to someone else's experiment and add another person's experiment, we have more trials. You see that not everybody has the same probability. The experimental probability can change depending on the number of trials and the fluctuation of results. You might have rolled 3 odd numbers, your friend might have rolled 6 odd numbers. Based on the experiment, the probability can change. And that's experimental probability. The probability is not constant. It depends on how many trials you've done. And when you add more trials together, you will probably notice that these percentages get closer to what you would expect, that 50% each. So to improve the accuracy of your experimental probability, increase the number of trials. So here's a dice simulator. You'll notice I'm just going to be rolling one dice, and let's say I do one roll. Well, I rolled a 1. Let's do another roll. I rolled a 3. I rolled a 6. Now, if I only did 3 trials, if I only rolled the dice 3 times, you would see that, well, there'd be a 0% probability that I roll a 2, a 0% probability that I'm going to roll a 4, based on my trials. But the more trials I do, let's do 10 more trials, you'll see that the number of times I roll each possible outcome increases. 10 more trials, 10 more trials, 10 more trials. Let's do 100 more trials, 10,000 more trials. You'll see the more trials that I do, I keep doing 10,000 more trials, the numbers start to even out, which is more what we expect. So this is just to illustrate the idea that the more trials, the more accurate your probability prediction is going to be. So let's work through some examples. Here's the first one. The results of rolling 2 six-sided dice 50 times are displayed in the given graph. Rolling a 1 and a 4 and a 3 and a 2 are two different blank, but the same blank. So this is practice using the terminology on the first page. Try and see if you can figure out. So of course I'm looking for the difference between outcome and event. These are two different outcomes, but they are the same event because they both are rolling a 5. How many trials were performed? Well, I told you in the question, the dice were rolled 50 times, so there's 50 trials. Which event seems most likely to occur? Well, the most likely to occur would be the one that occurred most often, which would be rolling a sum of 6. What is the experimental probability of rolling a sum of 6? Well, remember our formula, probability of rolling a 6 is the number of successful trials divided by the total number of trials. Well, how many times was a 6 rolled? 12 times. How many total trials were there? 50. So the probability of getting a sum of 6 is 12 out of 50. Now, of course, anytime you write a fraction, proper notation would be to write that fraction in lowest terms. So you'll notice these are both even numbers. 12 and 50 are both even. That means you can divide both of them by 2. So you can do that, and you end up with 6 out of 25. Now the question is 6 out of 25 lowest terms? Well, yes it is, because there's no other number that 6 and 25 are both divisible by. So this is lowest terms. And you can write that as a decimal. Go 6 divided by 25. It's 0.24. So the probability is 6 out of 25. It's also a probability of 0.24. And you can write that as a percent as well. This is 24%. What is the experimental probability of not rolling a sum of 6? Well, you could just add up all the trials that were not a 6. You could add those together to get the number of successful trials, divide by 50. Or you could just think of it this way. If it's 6 out of 25 to be a sum of 6, the rest are not 6. So if 6 of the 25 are 6, then that would mean 19 of the 25 are not 6. So the probability of not rolling a 6 is 19 out of 25. And you can change that into a decimal. 19 divided by 25 is 0.76, and that as a percent is 76%. What is the experimental probability of rolling a sum of 13? Be careful, it's not trying to be a trick question, it's just testing your understanding. A sum of 13 is not on the chart. Can you roll a sum of 13? No, you can't. The highest you can roll is a 12 with 2 dice. So what is the probability then? It's 0. What is the experimental probability of rolling a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12? Well, that's all the outcomes. So what's the probability that you're going to roll one of those outcomes? 1, or 100%. Now, some people get confused about the number 1 when we're talking about probability. If you add up all the trials that got one of these outcomes, all 50 trials would end up being one of those outcomes. So the probability would be 50 out of 50. If you reduce 50 over 50 to lowest terms, it'd be 1 over 1, which is 1. So that's where the number 1 comes from when we're talking about probability. The next example, a probability experiment was designed to find the expected number of females in a family of 5 children. To simulate the genders of the 5 children, a coin was tossed 5 times. Heads represented a male, tails represented a female. The experiment was repeated several times. The results are shown in the graph. So here we are. Let's try to understand this graph. I'm missing some numbers on the scale here. I just couldn't get the graphing software to do it for me. So let's fill them in. This is 0. That's 1, 2, 3, 4, 5. So how do we read this graph? Frequency. Frequency means the number of times something happens, or the number of times it occurs. So that means for a family with 5 children, there were 2 of those families that had 0 female children. There were 7 of those families that had 1 female child. 10 of those families had 2 female children. 5 families had 3 female children. 5 families had 4 female children. And there were no families with all 5 children being female. So how many trials were performed? Well, remember, trials are just the number of families that they're simulating. So we can just add up the number of trials for each, and that will give us the total number of trials. We've got 5 plus 5 is 10, plus another 10 is 20, 27, 29. There were 29 trials performed. What is the experimental probability of having 2 females in a family of 5 children? So we're trying to find the probability of having 2 female children. And remember the formula for probability, it's the number of successful trials divided by the number of total trials. Well, in this case, success would be having 2 female children. This outcome, how many times did that occur? 10 times. There were 10 successful trials out of the 29 trials. So the probability is 10 out of 29. And hopefully by now you know how to change this fraction into a decimal and change that decimal into a percent. Try it on your own. You should end up with 34%. So there's a 34% probability that there will be 2 female children of the 5 children in the family. According to this experiment, what is the average number of females in a family with 5 children? So notice it's asking us to find the average number of females per family. So if we want to find out females per family, we can write that as a fraction of number of female children divided by number of families. So to find the number of females, well, there were 2 families with 0 females, 7 families with 1 female, 10 families with 2 females, 5 families with 3 females, 5 families with 4 females, and 0 families with 5 females. So we can multiply the number of families by the number of females in that family, and then add up the total number of females. And there were 29 trials, so that's the total number of families. So when you do all this math, it ends up being 62 out of 29. But that doesn't really sound very helpful because the questions ask me, what's the average number of females in a family with 5 children? And if you answer 62 29ths, it doesn't really sound very helpful. So we can change this into the decimal version. If you go 62 divided by 29 in your calculator, you end up with about 2.1. So we would say, on average, there's 2.1 females per family. So I know there's a lot of terminology and notation with P and brackets and number of trials, total trials. You got to read graphs. You have to decipher what the question's asking. There's a lot of stuff going on in this lesson. If you have questions about any of it, please ask me for some help, and I'll come to you and do my best to help you. Otherwise, move on to the practice questions.